Good day, everybody. My name is Andrew Valgo. I'm the Vice President of Engineering for Power and Data Systems. And today we're going to talk about more electronic aircraft is for our components here at PDS. We've all of our products are either electric or electromechanical in nature. We started out originally with data acquisition and began to couple that with discrete outputs and turned into solid state products where we're now doing primary and secondary power distribution products. This is distributing electricity throughout the entire aircraft, both AC and DC. We really do have a follow the wires approach, and in early 2000s we expanded into power generation and generation control. So that's moving up toward the source, but then also moving down toward the loads. And you can see there we also have quite a number of actuators, motors, anything that's linear or rotary displacement, pumps, all different types of devices there. So that's our products, and that's where I'm coming from. One thing to note is I'm also the chairperson for SAE AE7, which is wire protected devices. So we have a little bit of insight in terms of where SAE thinks we're going in the next 3 to 5 years. This slide gives an overview, shows that really there's a shift away from mechanical and hydraulic systems, and that's good for us since we're electromechanical. But the other thing is going higher in voltage and higher in power. Things we're seeing is a shift from AC to DC power, and then also voltages as high as 2 kilovolts. You see on the bottom there, back in 2019, we had a meeting at AE7, and we're looking at classes where general aviation, regional jet, we're talking 500 kilowatts, 2 megawatts, and up to 2,000 volts for distribution. So what does that mean for us as a system integrator? It means a stricter specs for generation, for distribution and loads, in terms of noise, accuracy. It also means more power conversion. So we have this high voltage, but we may not have the products in the field yet to actually utilize that high voltage. So it means stepping down voltage to useful voltages with loads that exist today. Another thing is solid state switching. As you get to higher voltage, especially as you approach DC, wire protection, load control, monitoring. It's zero crossing on an AC signal was a little bit easier, but when you don't zero cross with DC, you have to worry about things like corona arcing and switch damage as you're switching the load on and off. The other thing is intelligent power management. Now that you can couple CPUs with the distribution system, you're able to monitor everything on the aircraft. We can tell when pilots recline the seats. We can tell when they deploy the flaps. We can tell when somebody uses the faucet in the sink. But we're monitoring the voltage and the current, doing trend monitoring, and able to understand the health and usage of the entire aircraft. So one of the things that we're seeing a shift, especially in the last 3 to 5 years, is really a move away from AC generation. Originally, you had an AC, simple AC generator, and what you would do is rectify that. Well, you take that raw power and you could use that right for pumps and motors and de-icing. But then the other thing you do is rectify it, still be a high voltage, and you use it for large loads. Maybe it's moving heavy loads like landing gear or all electric taxi, radar, maybe some high voltage actuators. But then you'd also take that same thing and run it through a transformer rectifier unit, and that would step down the voltage, and you'd end up having a lower voltage, and you may have thicker wires because you may still have some of those heavy loads there. But that's more for the common types of loads, the cockpit instrumentation displays, all the cabin power, things like that. Now, as we're moving into high voltage DC generation, that HVDC could be a battery or it could be the generator, but what you're producing is filtered DC output right from the go. So it's either rectified on the generator itself or as part of a generator control unit, and then that can be DC to DC converted, and then it can power the lower loads as well. But as you see on the bottom right, that little graph there, you can see the difference in power density and what kind of capability. And there is an advantage when you go DC to DC. You get a good weight to power to weight ratio there, showing that DC is really the way to go. So why haven't we been doing this all the time? So AC is really best for unregulated raw power. I mean, you have a simple motor, you can run pumps and motors and heating and things like that. But one of the things HVDC, let's just speak with 270 volts specifically compared to 28, you're looking at a wire weight difference of 30 times. So here's two wires in the middle there. One is 2 gauge, one is 18 gauge. They both deliver the same amount of power. So there's a huge weight advantage there in wire capacity. The other thing is, without having a lot of the AC switching, your noise emissions can go down greatly. The other thing is you can attach a battery to this type of power system, which means you can store that power, unlike an AC system. Um, I think, but the issues with HVDC is it brings safety concerns. You can't disconnect a powered DC load at high voltage without doing some sort of damage. You As far as maintenance procedures, people have to be careful handling that type of voltage, because you can really get hurt with it. The other thing is, there's going to be a need for a lot of solid state switching. Electromechanical switches just won't do. There's with the damage you do to the contacts and arcing, solid state switching is going to be a new thing. But beyond that, you're looking at wires, you're looking at laminations. Everything needs to be upped in voltage in order to withstand and not break down. And there's going to be a lot of things like partial discharge is going to be a new thing where you're looking at how much leakage current and how good your laminations or insulations are. So after all this, though, 28 volts will never go away, and it's always going to be there. So, but this is 270 is really the way to go. Just two quick points on that graph. On the right, you can see 270 volts has quite a bit of green, and the main differences between these is really being able to handle the safety aspects of 270. Other than that, there's advantages all the way throughout. You're looking at AC, and you have to worry about phase balancing, power factor, frequency variation, all kinds of harmonics. That kind of stuff can go away, but you got to really harness. You got to have the components available. You got to be able to handle the voltage safely, and worry about arc faults and transients. Manage that. SAE has added 3 new classes to their voltage spec. This is AE7, and you can see we used to only go up to around 600 volts, and now we're up to around 4,800 volts. And these are the classes. These are preliminary right now, but this is what we're looking at as we move into silicon carbide and gallium nitride switched elements. Just want to give 4 examples of just some things we're doing. Here's an example of a completely solid state ice protection system. This is doing the main rotor blade, the tail rotor blade, the windshields, all the SLE markers, everything that needs some sort of heat control. This is all being done smartly with processors, monitoring currents, and modulating heat to these surfaces to keep them cool. So you're talking 33 kVA in this system with a couple boxes, but it's all MOSFET technology. So there's an example of some high voltage switching, and this is going to increase in higher voltage. New systems have come out up to, with 540 volt type systems now. The second piece is going the other direction where you go into high current, and these are examples where we're replacing electromechanical contactors now with solid state, almost like remote control circuit breakers, but they have a processor and they're able to do a lot of the health monitoring and maintenance and give you a lot of data as well. But you can use them for main bus shedding or delivery of power to other secondary systems. Last slide is really 2 other examples. It's just an entire cabin heating system where you're trying to keep the temperature in the cabin within a couple degrees, no matter where you're sitting in the aircraft. So it involves, again, intelligent heat distribution control. It's microprocessor driven. And in here, you're having about 24 kVA of heaters throughout the system at 115 and 230 volts. And the bottom one is really getting into the high voltage markets. One of the things is finding the right technology. A lot of new MOSFET technology in the last 4 or 5 years, and it's finding the ones that have the best DVDT, the best DIDT in terms of handling voltage slew and current slew rates. And this is an example of a pump that we've produced now where we're switching 270 volts with an 80 nanosecond slew rate, and we're switching it every 17 microseconds. So, of course, it needs a lot of filtering, but what we have now is something that we can control the speed, and we can current limit the power to this pump, which gives us a lot more safety, but also produces a very lightweight system as well.